Good morning from Hawaii. My name is Ashley Santos. I'm a graduate student at the Institute for Astronomy at the University of Hawaii. And today I'll be discussing something that I've been thinking about since I started grad school over 4 years ago, which is systematically searching for oscillations in exoplanet hosts with Kepler, K2, and TESS. But before I start talking about any results, I figured I'd start with a crash course into asteroseismology or characterized. I know this is a horrible joke, but I couldn't help myself because my name is in it and I'm discussing it anyway. Specifically for this brief summary, I wanted to start with an example that really showcases the synergy between astroseismology and exoplanet science. To do so, I'll start with a phase-folded light curve for Kepler 36. The best fit model is shown in red, which is centered around the primary transit, and the depth is an indirect measurement of the ratio of the sizes of the planet and star through basic geometry. Now, on the other hand, a Fourier transform of the out-of-transit data can be used to calculate a power spectrum of the star, which is shown in the bottom plot. A basic global astroseismic analysis of these higher frequency solar-like oscillations provides a stellar mass and radius, which can then be combined with this ratio to obtain a very accurate and precise planet radius. And the important thing I'd like to point out is that this is just one example where astroseismology works together with exoplanet science. In reality, we know that astroseismic analyses provide a full suite of precise stellar properties, all of which are important for understanding the planets that orbit them. Specifically, ensemble studies generally yield uncertainties of 1% radius, 3% mass, and 15% in age. I've also listed the stellar density here as well because I know that provides an additional constraint when you're modeling transiting exoplanets. Okay, so speaking of transiting planets, I think I've basically given this away with the individual example, but I'd like to talk more broadly about the space-based photometric synergy between transiting exoplanets and oscillating stars. So let's start with the period radius distribution, planet size on the y-axis and the orbital period and days on the x-axis. This is using updated planet radii from Gaia DR2, thanks to another graduate student here at Hawaii, Travis Berger, where median uncertainty is about 7%. And now I'd like to highlight two important regions on this plot. The first is the hot Neptune desert, which was actually referred to as the hot super Earth desert at the time in a Nature paper by Mia Lundquist in 2016. The paper discusses the dearth of planets in this region, which is hypothesized to be the result of smaller planets that receive high incident flux from their host star and are not massive enough to hold onto their atmosphere and thus resulting in this dichotomy of planet types. The second is in a more recent paper by Vincent Van Eilen discussing that this effect extends to smaller planets at longer orbital periods and is commonly referred to as the photoevaporation valley. Now, I understand that there were predictions for the existence of this valley long before this paper was published, and I also understand that there are other theories for why this valley exists, and I don't want to discredit either of these or any of these, but that's not what this is meant to point out. Two of these papers have something very important in common, and that's that both were using the subset population of planets orbiting astroseismic stars. So there are two main seismic host catalogs from Kepler, the first of which was by Dan Huber in 2013, which used approximately half of the Kepler data, and then a follow-up study by Mia Lundquist, actually in this 2016 paper that I mentioned right here. So now I'm going to take the rest of the planets away for now so we can see the smaller sample more clearly. And here you can see that both of these regions of parameter space are in fact empty, but the numbers are still small. Collectively, I think the two catalogs account for about 100 planets. Now, the funny thing is that directly after Mia Lundquist's paper came out in 2016, there was a re-release of Kepler short-cadence data, and this coincided right at the beginning of my first year in grad school. So since my thesis advisor is the first author to one of the two catalogs, this ended up being my first project as a graduate student. So I went back through Kepler short-cadence data to, one, redetect oscillations in previously known hosts, and two, to potentially find new seismic hosts. So what I'm going to show now are preliminary results from that study. And I'd like to emphasize that these aren't just Kepler hosts, but these are also folding in new results from K2 and TESS. So first, I'd like to highlight one benchmark system from K2, which is K293, or probably more familiar to some of you as HIP 41378. So this is a confirmed 5-planet system where 3 outer planets are all on orbital periods that are longer than a single K2 campaign, but were serendipitously discovered in campaign 5, which I'm showing there on the left. Now, it was reobserved in short cadence in campaign 18, where K2 was doubly lucky and happened to reobserve 2 of these 3 outer planets, which is shown on the right. But because we now had short cadence data and thus the required cadence to be able to detect solar-like oscillations, a quick look at the power spectrum indeed revealed these beautiful p-mode oscillations shown in this plot here. The figure is taken directly from a paper by our collaborator Mikkel Lund, myself, and many others, and this was just last year, where we performed a detailed asteroseismic analysis to recharacterize both the star and the planet in this benchmark system. Did individual analysis of individual frequencies, which provided really precise stellar properties, measuring a radius and mass to better than 1 and 2% respectively. And we were also able to get an age of the system to better than 15%, yielding a final age of about 2 gigayears. All right, so going back to our new seismic hosts, I wanted to flash maybe one more system as a teaser. This is another multi-planet system, which has 4 confirmed planets, and 2 of these planets straddle the gap. Furthermore, we have lots of new RVs to add to our analysis to provide better constraints on the densities for these diverse planet types, and this is a great test bed for testing planet formation and evolution scenarios. Okay, so for the second main part of my talk, I'd like to discuss how asteroseismology can help the direct imaging community. And to do this, I'd like to start by showing the stellar take on a very well-known plot from the exoplanet community, which shows detections based on their distance and brightness. So we're taking a step back now and not only focusing on solar-like oscillations in planet hosts, but for all stars. So instead here on the y-axis is the star's size. Its distance is on the x-axis, and the points are weighted by their visual magnitude, which is shown in the reference, in the legend for reference. For some historical context, I've decided to start with the status of the field prior to space-based missions like Kepler and Corot, and this is shown in green. Right away, you can see that there are not many detections, and this is because early ground-based astroseismology suffered from many challenges and was therefore limited to the closest and brightest stars from the ground. But then Kepler came through and revolutionized the field with thousands of new detections. The caveat here, though, is that Kepler detections were faint and thus making it very difficult to follow up with other ground-based techniques. However, I'm sure as probably everyone knows, the recent and ongoing success of the TESS mission has provided another means for highly precise, high cadence, continuous photometry, which is important for astroseismology. TESS is more sensitive to the nearby solar neighborhood and is quickly bridging the gap between the faint distant Kepler targets with the bright nearby ground-based detections. And by the way, one important thing I'd like to point out is that this is preliminary and not the total TESS yields. In fact, we expect that TESS yields will be about a factor of 4 to 5 higher than that from Kepler, so stay tuned. Now, I'd like to draw your attention to solar-like stars, which I've roughly approximated between these dashed lines. So even with the thousands of detections, the number of true solar analogues with astroseismic constraints is still quite small. However, a particularly exciting new discovery from the TESS mission that I will now spend the rest of my time talking about is going to add one more point to this region, which is alpha Mensae. So this is the TESS astroseismic detection using TESS data of alpha Men, which is a nearby G7 dwarf at 10 parsecs, and now the closest star for which we have an astroseismic detection from space. And currently, as it stands now, this is still the coolest star from the nominal TESS mission with a seismic detection. So alpha Men was in TESS's southern continuous viewing zone. On the top, I'm showing the normalized light curve, which is colored by individual sector, and the astroseismic detection for alpha Men is shown in the bottom 2 plots in log-log space on the left and then in linear space on the right. I've delineated the region of power access due to oscillations, which you can see more clearly zoomed in on the right. So because of the pattern or this regular spacing of solar-like oscillations, the autocorrelation is a quite useful tool to quantitatively confirm solar-like oscillations, which I'm also showing on the inset on the right. So if you take a look at the frequency of the oscillations, you can see that these are pretty high compared to the ones that I've already shown. And this would be correct. In fact, the star is oscillating even faster than the very well-known 5-minute solar-like oscillations. For reference, has a new max of about 3090 microhertz. So this is oscillating a little bit higher and is therefore consistent with the later spectral type. So my talk is almost finished, and I haven't even discussed the most exciting part of the system, which is that Alpha Men is the host to a mid to late M dwarf. The image I'm showing here is directly from the original discovery paper in 2007. This, of course, makes the asteroseismic detection more valuable now that we can age date the M dwarf, assuming that the two are co-eval. And since M dwarfs are notorious for their slow evolution, a precise and accurate age for the system makes it a benchmark to calibrate other age relations, like, for instance, gyrochronology. And furthermore, the companion was resolved in Gaia DR2, providing a contrast, and if we combine that with the asteroseismic age, enables a detailed characterization of the late M dwarf, which currently using, based on its approximate mass now, lies on the cool side of the fully convective region. So for those that are interested in M dwarfs, I've listed some preliminary numbers, but the paper is nearing a submission date, so keep your eyes open for that. And finally, as a nearby true solar analog, this is a prime target for future direct imaging missions looking for true Earth analogs around sun-like stars. So to demonstrate this last point, and I just gave it away, I've selected a plot from Beloukov et al. 2015 with contrast on the y-axis and angular separation on the x-axis, where points are also here weighted by their brightness. So you may see your favorite directly imaged planets in the upper right-hand side, or if you're looking anywhere else, these are hypothetical Earths around nearby stars. Out of curiosity, I calculated what this would be for Alpha Men, and sure enough, there it is. So because this is highlighted in blue, this is suggesting that an Earth around something like Alpha Men would be detectable with the next generation of space-based imaging missions like LUVOIR or HAB-X. And of course, any and all are welcome to have a go. Ages are really important for direct imaging, and I am just out of time, so I'm going to leave up my summary slide. Take any questions. Thank you very much.